So with that in mind, we just went out to make a MOF to suck up CO2. And so we went for a MOF that had amine-lined pores. So here's the building block. So one of the other nice things about this approach, it's quite modular. So the components here, this is just a zinc ion. This is oxalic acid, which is, it's literally dirt cheap. It's the major component of a kidney stone, the organic component of a kidney stone. And this is sort of our building block. We like it's an amino triazolate. The exact structure isn't that important. Other than that, it has this is an NH2 group. So this is an amine group. And when we link this into a network, what we see is here is a nanoscale pore. It's about 0.5 nanometer in size. And then there's these blue spheres here are the NH2 groups that are pointing right into the pore. And this so this is one layer. And then the oxalate, the kidney stone component, comes in and links that later. So this is flipped 90 degrees into that, and it forms this three-dimensional pore structure. Okay, so as far as the gas sorption, we were really happy to see. So the different plots here, for carbon dioxide, the two plots are the blue and the red ones. So the red is at room temperature and the blue is at 0 degrees. So what we see is that this solid takes up CO2 really well. The only other thing it took up, this is hydrogen, but this is hydrogen down at 87 degrees Kelvin. So that's really not a practical temperature. But so interesting things here, nitrogen, argon, these other gases, hydrogen at room temperature, they're not taken up at all. Okay, so it's quite selective. So there's a number of interesting things. So good selectivity. The other thing is, so this graph is amount adsorbed versus pressure. So we see very good uptake at very low partial pressures of CO2. We see 20% difference or so just by a temperature swing of 20 degrees Celsius. So we're quite excited about the use of these as potential pressure swing adsorbent materials or combination pressure temperature swing adsorbents. Okay. The other thing that was interesting, so you do that same experiment. So again, here's the CO2 uptake plot. This plot shows there's two curves here. There's a filled sphere and an unfilled sphere. So the filled one is the sorption and the blank one is the desorption. So what you see is that it's easy on and easy off. There's no heating to over 100 degrees to remove the carbon dioxide. You apply a vacuum and it comes off again. Okay, and so that's because we're not forming a covalent bond. This is a physisorption, not a chemisorption. Doing this experiment at a few temperatures, you can get this a plot of delta H adsorption. So this is heat of adsorption. This is just a measure of the affinity. So something that was really interesting here was that this curve, a lot of papers will plot this and it just drops down like that. So essentially with coverage, what I was saying how you'd want one layer to polarize the next layer, well that effect just gets insulated the further out you go. So typically with coverage, you expect that to drop down. In our case, it dropped down a little bit and then it went back up. So this is 40 kilojoules per mole. Compare that to a covalent bond, which is over 100 kilojoules per mole. But it's a strong physisorptive interaction. I think the highest CO2 sorption that's been reported is in zeolite NaX, which is 48 kilojoules per mole. And so we're in the neighborhood of 38 to 41. We actually have one now in the lab that has a delta H of 52. But this is an interesting phenomenon. Okay, so why did that happen? So I mentioned one of the nice things about these compounds is that they're crystalline. So this is, again, an X-ray structure. So an actual picture of the molecule. There's an actual pore. So here's that NH2 group. And so if you remember your first year chemistry, oxygen's more electronegative than carbon. So in a CO2 molecule, you've got a little bit of negative charge on each oxygen and a little bit of positive on the carbon. So there's that amine group. And so that the electron pair on that nitrogen is pointing right at the partially positive carbon of the CO2 molecule. This partially negative is pointing right at the carbon of another CO2 molecule. So this is exactly what you'd think would happen in terms of the positive, negative, favorable interactions. But this also makes sense for why the adsorption goes up with loading, because this one it's quite the binding of the first CO2 helps the binding of the second. Okay, so this is just one compound. We're making entire families of these. With this particular family, there's lots of options for modular variation, so just switching out components. For this whole area, Aldrich Chemicals just started selling them. BASF is making them, Aldrich is selling them. They call this basalite. But none of the compounds that are being sold commercially have amine groups for CO2 absorption. That's something that this paper, we published our first paper last year, and we've got a string of them coming out now that are going to be quite high impact. So, I put here, this doesn't mean it's a mature technology. BASF's take on why they wanted to start selling these was that they view these compounds as having so much promise, they just wanted to get them in the hands of people who can't make them. Okay, so that's the first part of what I wanted to tell you about. This one will be really quick. Just talking about these materials, same class of materials as fuel cell membranes. So PEM fuel cells, these are the fuel cells that would run on hydrogen and run on methanol. But basically, the component we're looking at, any fuel cell, you've got fuel comes in and is oxidized at an anode. So here, hydrogen, you form an electron and a proton. The proton has to migrate through an electrolyte material, and then it'll recombine with the electron at the cathode, but this is where you get your electricity from. The proton then will combine with oxygen on the cathode to complete your cell. So this material here really defines the performance of the fuel cell. Okay, so the industry standard are these things like Nafion polymers. So this is like basically sulfonated Teflon. Okay, so so we're talking about mobility, something that should enable mobility in a solid. So people have always taken mobility and disorder to go hand in hand. You don't think of something ordered as enabling mobility. So the area of research we were working on, well, let me just say, this is how a proton actually moves through that. One, it can either move through the sulfonic acid groups, just kind of hopping between them, or the sulfonic acid groups can anchor water, and the proton will just hop between water molecules. Okay? Or it could actually just be a hydronium that moves, but that's actually the slow way. This is the fast way here. So for these membrane materials, this is what you want. The key ones here, a lot of these are core, but a key one is that you'd like it to work at above 130 degrees Celsius. And the reason for that is the kinetics of the fuel cell get better, okay? Okay, one more minute. The kinetics of the fuel cell get better. So this is then our approach. So this is, again, a crystal structure of one of these materials. And I'll just jump ahead. The exact composition isn't that important. But I mentioned water can carry the proton. You can also put a molecule in those pores that can hop a proton, but is obviously something that's less volatile. And with that, here's the conductivity in the presence of water. So drops off at about 80 degrees, you start lose water, and this is not great conductivity, and it gets worse. You'd like this to be at least around 10 to the minus 3. With that other molecule in there, we're getting close to 10 to the minus 3, but importantly, it's at 150 degrees Celsius. Okay, so this is something then that our group pioneered this approach, and we published our first paper on this so Nature Chemistry is the top chemistry journal in the world, so we were the cover of that in December. That was published. So that's essentially the two main thrusts of research going on in my research group, and I'll be around till early afternoon if anybody would like to talk, and every academic is always looking for more money. So thank you very much.